A few years ago I bought this transistor tester. Made by Fish 8840. It was made in China. And of course it had software inside. It was no success because it worked only approximately 4 years. And then it suddenly stopped. So, very strange. Had not expected that at all. It's a transistor tester, capacitor tester, coil tester, etc. etc. But it stopped functioning. So that was a problem. So I had to go back to the old school schematics. And that's why I made this capacitor tester working in the range from say 2 picofarad up to 1.5 microfarad. So quite a big range. And at first I want to show the schematic. And the schematic is here. This is, by the way, the best setup. I made some adaptations and I will show them. It is in fact a very simple circuit. I've used a TL071 op-amp. That's an op-amp with field effect transistor input. And it creates a very stable square wave. A very good, very proper, sharp square wave. And that part of the circuit is here. And I needed a square wave of 2.5 kilocycles. And that's generated here by the use of this capacitor 3300 picofarad. That makes that this circuit oscillates on 2.5 kilocycles. And then we send that square wave through the capacitor under test. And here we have the op-amp with the meter, the Micro Ampère meter, in the collector lead. And of course you can see that you can align that meter here. Calibrate it to by anti-parallel diodes to protect the meter. And furthermore, there's nothing more to tell about this circuit. And it works very properly. And I want to show that. And here we set the sensitivity of this circuit. That's done here by a switch with 4 positions. At first the circuit is open, the most sensitive setting of the meter. It goes from 2 picofarad up to say 3000 picofarad. A somewhat less sensitive setting, 1K. That's the range 3 nanofarad up to 68 nanofarad. And here a 100 ohm resistor. The range 50 nanofarad up to 470 nanofarad. So 0.47 microfarad. And here the less sensitive range. And you have to do some experiments with this resistor to find out the proper value. I measured it 70 ohms, but I will show more of the circuit, how I made it in real. Pin connections, more relevant information. The microampere meter here that I used has a DC resistance of approximately 1000 ohms and is a pure professional meter from the United States, made in 1979, so a long time ago, but it still functions completely properly, of course, because it's high quality. And originally this unit was a laser power meter. That was the aim of this meter. But now it's a capacitor tester. So 1000 ohms is a good value for such a meter, and the good thing of it all, that it has such a big scale. Of course, you can also use in this schematic such a small meter. They were often used in the 1980s, 1990s as tuning, to tune into a radio station on FM and measure the resistance of that meter. You can measure that here. And when it is between, say, 600 ohms and 1000 ohms or 300 ohms also will do, it's usable. Of course, with such a tiny scale, it will be quite a problem to write all the capacitor values on the scale and after all read it out anyway. I've used here that beautiful professional meter, and I've written here on the scale all the capacitor values. I calibrated it in a very simple way by taking capacitors out of my storage, and here, and sometimes 2 of them or 3 of them, and then let the pointer move in the right sensitivity range, and then write all the values on these scales. I've made a circuit not with this switch 1, with 4 positions, but with 2 normal switches called A and B, and you can set these 2 switches to certain positions. So here up, in the middle, or down, and here up and down, and with that by that way I switch on the sensitivity of the scale of the meter. I want to show that part of the circuit is here, and this is the way that I realized it, though the first idea that I showed is, in my opinion, better, with a switch with 1 motor contact and 4 positions. But anyway, when you cannot find such a switch, you can use this option. That's the way how I made it. And you can see here that in fact we have the open position of that switch. This switch has a middle position, and when in the middle position no connections are made between the upper electrode and the down electrode, so that's good, useful in this circuit. So this is the middle position. The circuit is open and is maximum sensitive, and by moving the switch to this position and that position, you switch in other resistors, making that input circuit with that Darlington less sensitive. So you can read it how this works. I have to say that. Here is the circuit, by the way. Power supply made with a 7812 12 volt regulator, positive regulator, two very tiny transformers, as tiny as possible, to keep the stray fields as small as possible, because we have here a meter that can pick up the stray field. But it was no problem, it worked. Here is the square wave oscillator, and I've used here in the Darlington circuit that drives the meter not a 100k potentiometer, but fixed value resistors. Of course, that was all tested properly first, and these are the fixed value resistors that you can use. 39k, 47k, 470k. Of course, these two are in series. So that's also an option that can be used instead of that potentiometer that was visible on the other side and that I showed earlier. Again, this part of the circuit. Here again the circuit. And here you see that 100k potentiometer. You can use that surely also, but you will find that you have to set that 100k potentiometer into a fixed position. So that means that it is better in a certain way to use fixed value resistors, because such a potentiometer can get a somewhat other value due to aging, etc., etc. So fixed value resistors are in fact preferred. So let's finally look again at the circuit. Here the potentiometer connected to the Micro Ampère meter, with which you can calibrate. And furthermore, there's not so much more to tell. I've drawn in all the values of the capacitor, so I had to take that glass unit here off, and that meant that the pointer of the meter got very, very sensitive. So when you get close with your hands to that meter, the pointer will move. So it's a quite critical way to calibrate it and test it and write in all these values, but anyway, it worked, so be very careful when you do that. Now, testing a 10 nanofarad capacitor. And that means that we are in this scale. A up, B up. Both capacitors up. Sorry, capacitors, switches up here. Means that this capacitor must give out 10 nanofarad. So that's the green scale. And you can read here that it is approximately 10 nanofarad. So useful circuit, I think, and it can last for many, many years.